Hello, my name is John Williams and I'd like to welcome you to this short presentation on the design of hydrodynamic journal bearings. This is the second webinar organised by the Institution of Mechanical Engineers on bearing design. The first, on the design and operation of rolling element bearings, was given by my colleague David Cornell in 2018. It is still available on the IMechE website. Both David and I are members of the Tribology Group committee of the institution. A bearing is an assembly of components designed to allow the easy relative motion of two machine parts while carrying an applied load. We can classify bearings either by their geometry or their mode of operation. Linear bearings support loads that are perpendicular to the direction of sliding, so are appropriate for mechanisms involving linear motion. Thrust bearings are those that can support an axial load between components that rotate relative to one another. Radial or journal bearings support a radial load between rotating components, and it is these that we're going to look at in more detail. In any bearing, it's important to physically separate the opposing materials of which the moving components are made. If unprotected sliding metals come into contact while carrying a load, friction and wear levels are likely to be unacceptably high. In the simplest form of journal bearing, the shaft or journal rotates without additional lubrication within a sleeve or bush, often made of some sort of polymer. Protection comes from a very thin layer of the polymer, PTFE is an example, that is transferred from the bush to the shaft. Interposing rolling elements between the shaft and the housing gives rise to rolling element bearings. Although now there is no gross sliding between the balls or rollers and the races, these must be lubricated because of the very high local pressures, typically of the order of gigapascals. In both hydrostatic and hydrodynamic journal bearings, solid-solid sliding is replaced by shear within a low shear strength lubricant film, introduced between the solid surfaces. The pressure in the film must be sufficient to carry the radial load. In hydrostatic bearings, this pressure is generated by an external pump that supplies the bearing with the necessary flow. In hydrodynamic bearings, also sometimes known as full film bearings, the pressure is generated within the bearing itself. It is self-acting. The bearing must still be provided with a supply of lubricant, but this can be at a pressure much lower than that which would be required to support the load. Rolling element bearings and many other important tribological contacts, such as gear teeth, cams and followers, and other non-conformal contact geometries, rely on elastohydrodynamic lubrication. Under very high contact pressures, the viscosity of a hydrocarbon or oil-based lubricant can be very greatly enhanced, and in addition there will be local flattening of the metal surfaces. Elastohydrodynamic analyses can predict bearing behavior taking account of both of these factors. Boundary film bearings are those in which the required film of lubricant is not supplied continuously to the bearing, but is gradually exuded out of a porous and previously impregnated sleeve. Porous bronze bushings used for light duties exemplify this form of journal bearing. When choosing which form of bearing to use for a particular application, it's important to remember what limits the performance of each type, and to match the characteristics of the bearing, usually load and speed, to that of the application. This and the following slide illustrate some of these limitations. Dry bearings are usually limited by thermal considerations. If either load or speed is too high, then a polymer bush can soften and distort. The life of rolling element bearings is invariably limited by fatigue of one of the races. The location of the fatigue failure can be either beneath the surface of the material or at the surface, initiated perhaps by over-rolling a hard particle. The limiting loads and speeds of full film bearings can depend on the initiation of cavitation in the liquid film or on a reduction in the effective viscosity of the lubricant because of excessive temperatures. Of course, hard and abrasive foreign bodies in the lubricant, perhaps ingested from the external environment and not filtered out, can lead to much reduced bearing life through abrasion of the bearing surfaces. A rather busy slide, but one which compares the load speed characteristics for three types of journal bearings: dry bearings, rolling elements and hydrodynamic bearings on axes of rotational speed n plotted horizontally and load W vertically. We're going to express rotational speed in revolutions per second. Whenever you look up rotational speed, be careful about the units. These might be in rows per second, radians per second, or even RPM. On this graph, both axes are logarithmic scales. The scale on the top shows speed as RPM, and the load scale on the left is in newtons and on the right in pounds force. For a dry bearing, in the highlighted case, an acetal bush of diameter D of 50 mm and length or breadth also 50 mm, the load carrying capacity falls away at quite modest speeds. This is to prevent excessive softening of the polymer. For a rolling element bearing, again of diameter 50 mm, the load capacity falls away rather less steeply. The load speed curve is rather flatter. The characteristic of a hydrodynamic bearing is different. This curve is also plotted on the basis that the axial length of the bearing B is the same as its diameter D. In other words, the footprint of the bearing is square. The load carrying capacity of this bearing builds up with speed to a maximum at a rotational speed of about 80 revolutions per second, or 4,800 RPM. With a further increase in speed, the load capacity falls away. This is principally because of the effect of temperature on the effective viscosity of the lubricant, that we assume is a medium-grade hydrocarbon oil. At high speeds, the very high rates of shear in the oil increases its temperature, and so its viscosity falls. This limits the load capacity of the bearing. We want to ensure that the relative motion between journal and bearing is accommodated within the oil film, and that the solid surfaces themselves do not come into contact. If they were to do so, then there would be mechanical damage to at least one of them. In the next few slides, we examine the underlying mechanism on which hydrodynamic bearings depend and look at a couple of practical examples. Then I will mention some of the limitations to which hydrodynamic bearings can be subject, and finally mention some of the publicly available sources of further information on their design and application. Imagine for a moment a dry or unlubricated bearing in which the shaft or journal supports a load W acting vertically down, perhaps a gravity load. Now suppose the journal starts to rotate in a clockwise direction. Dry friction between the shaft and the bearing will allow the journal to climb up the bearing so that the point of contact is displaced, as shown. Now add some viscous lubricant. The relative motion of the turning shaft in the stationary bearing will draw in some of the lube into the converging gap. As liquids are very nearly incompressible, then a pressure is built up in the film that forces the shaft to move away from the bearing, to the left, to such an extent that the position where the oil film is thinnest, shown as IMechE, is actually to the left of the line load. It is this pressure that provides the load carrying capacity of the bearing. Notice that the centre of the shaft or journal is offset from the centre of the bush or bearing. This is what happens in a hydrodynamic bearing. All such bearings must have the right sort of convergent wedge geometry, an adequate supply of viscous lubricant, and a relative motion between the surfaces that acts to pull the lubricant into the gap. At the other side of IMechE, the gap must be diverging, and here the pressure in the film falls. In principle, it could go negative, that is below atmospheric, but in practice, the oil film cavitates and breaks up. This slide summarizes these conditions. Bearing operation depends on shearing the film of viscous lubricant in the clearance space between the bearing, that is the bush, and the journal. Continuous rotation of the journal entrains lubricant. If this is effectively incompressible, then a positive pressure is built up, which can support the radial load. The bearing will always run with some eccentricity, that is, the centers of the journal and the bearing are displaced. In general, the minimum film thickness will not be on the line of the load. The value of Hmin is obviously of interest. Real surfaces, even bearings, are not perfectly smooth, and so Hmin must be sufficient to ensure that there is no solid-solid contact. For confidence that this will not happen, the minimum film thickness should be several times the roughness, or RA values, of the journal and the bearing surfaces. That is, say Hmin is greater than, say, 5 RA. The ratio of minimum film thickness to surface roughness is sometimes referred to as the lambda ratio. In the same way, no lubricant is perfectly clean, and so Hmin must be at least as large as the largest contaminant particle that the lubricant might contain. The analysis of this sort of situation was first completed by Osborne Reynolds back in the 1880s. All subsequent analyses, or numerical models, use the same ideas, and the governing equation is known as Reynolds' equation. This slide illustrates two sorts of hydrodynamic bearings. The journal bearing, which we can see the lower half, is of dimensions B by D, and in this case carries a steady downward load. You can see the oil supply groove that is situated away from the arc of the bearing in which the fluid will be under a hydrodynamic pressure. Oil must be supplied at sufficient rate to compensate for its loss from the ends of the bearing. The ring of 11 more or less square pads are designed to carry the axial load. They are tilting pad thrust bearings. We won't talk about their design in this session, but they too depend essentially on the same mechanism, and are described as suitable form of Reynolds' equation. A few more bullet points. As the shaft rotates, there will be a flow of lubricant from inlet to outlet. The bearing must be supplied with oil at a sufficient volume flow rate to compensate for this leakage, usually by pumping oil to axial or circumferential grooves in the bearing surfaces. Oil is too valuable to waste, so that lubricant has passed through the bearing must be collected, filtered and recirculated. These notes are relevant to situations where the load is steady in magnitude and direction, or at least varies rather slowly. Where there are dynamic conditions, for example in the bearings within an internal combustion engine, then a more sophisticated treatment is required. Another quite busy slide showing a sketch of a journal bearing carrying a vertical load W supplied with a viscous lubricant. The eccentricity E, which is the displacement of the journal center from the bearing center, generates the convergent wedge geometry, and the shaft rotation gives the entraining velocity. Diagrams of this sort always greatly exaggerate the difference in dimension between journal and bearing. In reality, the radial clearance C, that is the difference between the radii of the shaft and the bush, is about 1 part in 1,000. Here the load is again assumed vertically down, and the pressure in the convergent wedge pushes the center of the journal to the left, so that Hmin is not in line with the load. The angle phi between the load line and the position of the thinnest oil film is called the attitude angle. Note too that the oil film extends a little way beyond Hmin into the divergent zone before the liquid cavitates. Engineers rather like non-dimensional numbers, and one that is often associated with journal bearings is the Sommerfeld number S. This includes information about load W, dimensions B and D, that is 2R, clearance C, rotational speed N, and lubricant viscosity eta. It is usually defined as shown. Note that since load W is on the bottom, increasing the load moves to smaller values of S. The various curves are drawn from different values of B upon D and enable us to read off an estimate of the eccentricity ratio, that is E upon C, or equally H min upon C. Sensible designs are generally within the area shown. If the bearing is too short, then much of the oil supply is wasted in that it carries little load. If the bearing is too long, there can be alignment problems. And if H min is too small, there is a danger of solid-solid contact, and so damage to the bearing surfaces. We have seen that hydrodynamic bearings work because of two important properties of a fluid. Firstly, viscosity, and secondly, the fact that liquids are almost incompressible. The formal definition of viscosity is illustrated by the diagram. Imagine two plates of unit area separated by an oil film of thickness h. The lower plate is stationary and the upper moves to the right at speed v. The shear stress needed to maintain this motion is torr. This stress is related to the velocity gradient, that is, the quantity v upon h, and is given by the formula shown, where eta is the viscosity. It will have units Newton-second per square metre, or Pascal seconds, or if you prefer, kilograms per metre per second. In the now old-fashioned centimetre-gram-second system of units, the unit of viscosity was given a name, the poise, and this unit is still quite often used in publications. It turns out that water has a viscosity close to 1 centipoise, that is 1/100th of a poise. In SI units, 1 centipoise is equal to 1 millipascal second. A typical mineral oil is about 100 times more viscous than water, and air about 100 times less. The so-called kinematic viscosity is defined as viscosity divided by density, and in the CGS system, the unit is called the stoke. Since mineral oils have a density or specific gravity of just less than 1, the numerical value of the viscosity of an oil in centipoise is quite close to the numerical value of its kinematic viscosity in centistoke. The viscosity of an industrial hydrocarbon lubricant is very dependent on its temperature, as is illustrated by the data of this slide. The ISO, that is the International Standards Organization viscosity grade number, refers to the viscosity measured in centistokes at a temperature of 40 degrees centigrade. The higher the VG number, the more viscous the lubricant. For hydrocarbon oils, the numerical value of the kinematic viscosity in centistokes is very close to the absolute viscosity in millipascal second. An alternative, and perhaps more familiar viscosity grading system, is the SAE, or Society of Automobile Engineers, number. There are conversion charts on the web to convert from one system to another. A multigrade oil, such as 5W20, behaves with a lower viscosity in the winter, W, taken as 0 degrees Fahrenheit or minus 18 degrees centigrade, and the higher number at high temperatures, that is 100 degrees centigrade or 212 degrees Fahrenheit. The outer surface of most plain bearings is coated with a thin layer of a soft, low melting point alloy, often called either white metal or babbitt. This alloy can include tin, lead, zinc and bismuth. Not so much lead these days. It is there to act as a final protection against dramatic failure, if, for some reason, the lubrication system were to fail and the bearing becomes starved of oil. The alloy softens or melts and prevents gross seizure and potential dramatic machine failure. Usually the diameter D of the shaft is known, having been dictated by strength or stiffness requirements elsewhere in the machine. We assume the load W is known, so that we need to specify the active bearing width B. In general, the nominal pressure, that is the load divided by the bearing footprint, so W over BD, should not exceed 4 megapascals. If the machine is subject to a lot of starts and stops while still carrying the design load, then this nominal pressure should be much less, perhaps down to about 1.3 megapascals. If the bearing is too long, say with length more than its diameter, then there can be alignment problems, so that again, in general, dimension B should be less than diameter D. The lubricant supply pockets can be either axial or circumferential. If the direction of the load does not vary, or varies only over a small angle, then it's sensible to choose to supply the lubricant from one or two axial grooves or pockets, as illustrated. Knowing W, D and speed n, the figure gives some guidance on suitable values of the ratio of B to D. For a given value of D times n, the operating point of the bearing should not be above the appropriate curve for the given ratio of B to D. If the load varies over a rather larger angle, then it may be preferable to supply the lubricant from a circumferential groove. This effectively splits the bearing into two narrower journals. Again, if we know W, B, D and N, then the graph indicates the maximum acceptable value of a specific load, W over BD. The width of the groove or pocket, dimension A, should be about D upon 10, and its depth about D upon 30. Let's look at a numerical example. Suppose we have a steady load of 10 kilonewtons supported on a shaft rotating at a steady speed of 3,000 revolutions per minute, so 50 revs per second. We choose an axial oil pocket, so the curves of slide 17 apply. Suppose we take D equal to 76 millimeters, or 0.076 meters, then D times N is equal to 3.8 meters revolutions per second, and W upon D squared is equal to 1.73 megapascals. This plots as the point shown, so this suggests that a B upon D value of 0.5 will be fine, so that B equals 38 millimeters. We just check the value of the specific load, that is W upon BD, which will be 3.46 megapascals, so less than 4. All okay, especially as the startup load is only 10% of the running load. We can estimate the minimum film thickness by evaluating the Sommerfeld number. Let's suppose that we choose a ratio of R to C of 500, so the radial clearance is 38 millimeters over 500, in other words 76 microns. Then if we take the lubricant viscosity at 30 millipascal seconds, that's equivalent to an ISO viscosity grade 46 at 50 degrees centigrade, the Sommerfeld number works out at 0.68. Since B upon D is equal to 0.5, the operating point is about here, which means that H min upon C is about 0.2, or that H min is equal to 15 microns. That's pretty generous, much more than the likely surface roughness of the components, and if the oil is filtered, larger than any bits of grit or dirt that are likely to get through. Now suppose we were to reduce the clearance by a factor 2, so that it reduces to 38 microns. Then, since the Sommerfeld number depends on R upon C squared, the value of S increases by a factor of 4, and the operating point moves to here. Now H min upon C is equal to 0.55, and 0.55 times 38 is about 21 microns. So that by making our components such that there is a reduced clearance, the minimum film thickness has actually increased. As a second example, consider this case. The load is 1500 newtons, but it can rotate with respect to the shaft, which is turning at 1000 rpm, or 16.7 revs per second. The diameter is 45 millimeters. Now we need a circumferential groove or pocket. E times n is 0.045 times 16.7, which is 0.75 meters revolutions per second. And so looking at the figure on slide 18, the maximum nominal pressure should be about 1.3 megapascals. Thus an active bearing width B of 26 millimeters. The groove might be about 5 millimeters wide, so the whole bearing will occupy a length of around 31 millimeters. It's always useful to have an idea of how much torque the bearing is absorbing, and thus how much energy is being expended in shearing the oil film. The Petrov equation can provide a quick estimate. This is based on the idea that the fluid film fully occupies the gap between the journal and the bearing, but that the shaft is running concentrically. Although we know that once a load is applied there must be some eccentricity, the Petrov estimate is still useful. Using the data of example 1, an estimate of the torque, T, comes out at around 1.62 Newton meters, and the absorbed power at about 500 watts. More accurate estimates can be made by allowing for the eccentricity of the journal and the variation in temperature of the lubricant. ESDU Guide 84031 has a suggested procedure. The previous examples have suggested methods for the design of steadily loaded fluid film journal bearings operating in the safe region. If we increase either load or speed, or both, beyond some limit, then difficulties may arise. Keeping the speed constant but increasing load will, as we have seen, lead to a reduction in fluid film thickness, so there is always a danger of metal-to-metal contact, with ensuing problems of damage. At modest loads but high speeds, there can be dynamic instabilities in the oil film, leading to the initiation of vibrations. In addition, the very high shear rates imposed on the oil can lead to a reduction of its viscosity as the long hydrocarbon chains are broken. Increasing load and speed together will mean that more energy is being injected into the oil film, so that the temperature of the assembly will rise, perhaps to unacceptable limits, because of softening of the protective white metal layer or excessive oxidation of the lubricant. There is a wealth of more detailed advice on bearing design readily available. The Tribology Handbook has a lot of very practical information, as do the Engineering Sciences Data Unit publications. Both include ways of calculating flow rates and of estimating temperature increases in steadily running bearings. The Tribology Group of the IMechE has generated some online guides on a number of tribological topics, including bearing design. You can find them on the IMechE website. To summarize then, hydrodynamic bearings must have the right geometry, a convergent wedge, be supplied with an adequate flow of viscous lubricant. The bearing surfaces must have the correct relative entraining velocity to pull the lubricant into the contact. All these conditions are met in journal bearings. Of course, there is more to the topic than we have been able to cover. Real lubricants can have a more complicated rheology than the simple Newtonian behavior that we have assumed. The energy that the bearing absorbs increases the temperature of the oil, and that will reduce its viscosity, so that the film thickness will fall. To get more accurate estimates of bearing behavior, it may be necessary to solve the thermal problem represented by the bearing and its housing. There is some guidance on these factors in the suggested references. Real component surfaces can never be perfectly smooth, but must have some roughness, and this might be of the same order as the lubricating film thickness. In other words, the lambda ratio approaches the value 1. Real materials are not infinitely stiff. Under high enough pressures, their surface profiles can change. Although this is unlikely to occur in conventional journal bearings using metallic materials, it may happen with softer polymeric components. This is the regime of elasto-hydrodynamic lubrication, and again there is guidance to these more advanced ideas in the suggested literature. The situation will also be more complicated if the load is non-steady, but varies in either magnitude or direction, or perhaps both. The behavior of the film is still essentially governed by Reynolds' equation, but now relatively simple analytical solutions are no longer possible, and we must seek numerical solutions. These are beyond the scope of these introductory ideas.
Thank you very much for that, John. Good afternoon, everybody. Thank you very much for that, John. Good afternoon, everybody. My name is Dr. Abimbola Ladukon. Today I'll be taking the question and answer session. I've already seen a question or two on the platform, and I'll put that across to John. Please put forward your questions, and we'll go through them one by one. We've got about 28 minutes on this platform. So, John, I've got a question here that about one of the slides, and it's saying that why is the W over BD ratio, why should it be less than 4 megapascal? What's the need for that number, or slash where's it coming from?
Okay, well, the key thing, of course, in any bearing, any lubricated bearing, is to make certain that the solid surfaces don't come into contact. And the limit of 4 megapascals, or that sort of number, using conventional materials and conventional hydrocarbon lubricants, is a rough guide to that requirement. It's not a hard and fast rule, but it's a sort of first rough calculation to see if you're in the right ballpark.
Okay, but I mean, do we find in practical applications that people design beyond 4 megapascal and
sure. Well, not in we're talking about full film fluid bearings. In elasto-hydrodynamic lubrication, one of course can get very, very much higher pressures, nominal pressures, or pressures which can be of the order of gigapascals. But that's when one has to start thinking about the effect of pressure on the viscosity of the lubricant and the change in geometry of the metallic components that those very high pressures can generate.
Yeah. Thank you for that, John. Another question I've got here is there a simple equation to predict the oil flow requirement of a plain journal bearing?
Well, I suppose one can do a rough calculation. If you can calculate, if we assume the bearing is just a slice of a very long bearing, then you can calculate without too much difficulty the volume flow rate across a section of the bearing. And the worst possibility, of course, is that you lose all of that. You have to supply that volumetric rate. But to do a more detailed calculation, it's certainly possible to do. It's certainly possible to do that. And in fact, in the ESDU guides or the Tribology handbook, there are design charts and so on which will indicate the kind of flow rate you need for a bearing of a given size and a given aspect ratio. Okay.
Thank you very much for that. I've got a slightly detailed question here. So the Duck Ha over here would like for you to comment on recent development on oil bearings, particularly ones that would be practical.
Sorry, what sort of bearings?
Recent development in oil bearings.
Okay.
Yeah, and particularly ones that would be practical, or do you think this technology has matured to the extent where little game-changing improvements can be seen?
Well, clearly it is a mature technology. Hydrodynamic bearings have been around for a long time. I suppose the recent development, we're all concerned about loss of energy, loss of making these things as efficient as possible, and therefore reducing the viscous losses. And the easiest way to do that, of course, is to reduce the viscosity of the fluid. But the penalty you pay for that is that you get thinner films. So that means you have to have more accurately machined components, smaller clearances, and better surface finishes, and so on. I was at a meeting of the institution just last week, and people were talking about. We're all used to the sort of viscosities of the engine, the oils we put in our car engines, coming down over the years. But I gather there are now engines being designed with 0W10 designation. Well, if you work out what the viscosity of a 0W10 oil is at about, say, 100 degrees centigrade at the operating temperature of an engine, it's only marginally more viscous than water. It is very, it is a very thin, low viscosity fluid.
Yeah.
But clearly that means that you reduce the pumping losses, the churning losses, the power required to pump it around the engine, and so on. But obviously cleanliness and good surface finish is critical under those conditions.
Yeah, absolutely. I mean, and I would imagine that the tribochemistry becomes absolutely important in that.
Yeah.
As well.
I think that I mentioned the protection on the oil on the bearings. I didn't say, but I think nowadays polymers are also used as a sort of last resort, as a surface on the bearing shells. Yeah.
Okay, wonderful. Thanks very much for that. So the next question here, I think by the same person that asked the initial question, was: is it possible to predict the side leakage? That's really the why you have to supply. In a sense, that is the same question, a very similar question to how do you predict the oil flow requirements. You supply the bearing with oil from the supply grooves, and that finds its way out at the ends of the bearing. So it's the same question really, and the more detailed design guides will provide guidance on the sort of flow rates. In other words, the kind of leakage that you get from the ends of the bearings. Yeah. And obviously the pressure has to fall to the gauge pressure has to fall to zero at the ends of the bearings, and so thin bearings, you pay for a certain amount of load carrying capacity by having rather narrow bearings, but they don't take up as much space. I mean, it's always a compromise. Okay. Just moving on very quickly. I've got another question here. For feed pad positioning and attitude angles, could you espouse the benefits and disadvantages of an advanced or retarded pad position with reference to IMechE?
If the bearing is running under steady conditions, then you can predict the attitude angle reasonably accurately. If the bearing is seeing varying loads and the loads varying in either magnitude or direction, then that will change. The essential thing is that you don't attempt to supply the bearing at the position in which it's going to have to need a high pressure to support the load. So consequently, if the load varies to a very large angle, you may want to go to a circumferential groove rather than an axial groove. But again, these are things that the more detailed guides will suggest.
Will respond upon. Okay.
guidance on such detailed matters.
Okay, so we've got a slightly more specific question here, and it's saying, so I'm currently simulating spiral groove bearings with deep grooves that do not allow for a wedge action to occur. Therefore, squeeze action is the only source of hydrodynamic pressure buildup. Is a pressure sustained in a lubricant due to squeeze action of around 30 megapascal small enough to neglect possible heating in the lubricant? Or are there other factors to consider, such as the eccentricity speed?
This is a spiral groove journal bearing, I take it. Yeah, well, I mean, these are rather specialized things. I mean, I think I think there is guidance there is literature on spiral groove bearings, on thrust bearings and journal bearings. But a full numerical solution is way beyond the sort of things we've been talking about this morning. And I have not talked about the squeeze film effect. The squeeze film effect is that pressure which is generated when the two surfaces move together in a direction normal to their surfaces, as it says, and when the fluid is squeezed. That can be significant, but is not really relevant in steadily loaded journal bearings. But if the load is changing relatively quickly, then it might be, could be, would be.
Okay. I hope that was a satisfactory response,
well,
Mohammed.
Yeah, not really, but we're talking about steadily loaded hydrodynamic journal bearings. Non-steady spiral groove bearings is, rather more complicated state of affairs.
Yeah, and like you said, I think there are in those specific kind of situations there are publications that are
there's a lot in there
directly addressing those questions. Yeah. Okay. So the next question here is, what are the major reasons for failure of bearings in internal combustion engines? Main bearings or connecting rod bearings?
Well, I think you'd have to ask an engine manufacturer. I mean, I suspect it's dirty oil, to be honest, and not changing the oil filter or leaving the air filter off. Engines are pretty well designed these days, and if you change the oil and you keep it clean, then they'll go on for a very long time. But if they get full of dirt, they won't. The surfaces will get damaged.
Yeah. And I guess that's where the HMN becomes a critical factor.
HMN is important, and if the diameter of the dirt or the hard particles from the environment, and the environment tends to be made of hard things, then that will do a lot of damage to the bearing surfaces. Yeah,
absolutely. So somebody here would like to know whether the slides for this webinar will be shared. I think these are going to be available on the IMechE website, is it? Am I right, John?
I presume so. I'm afraid I don't know. I guess they are, but I don't always find the IMechE website terribly easy to navigate. But they'll be there somewhere, I think. Yes.
Okay. So I mean, we will be putting that in discussion in the next IMechE meeting.
Yeah.
And to see how we can get this on the website and accessible to as many people as possible. Moving on. The other question we've got here is, can we use water as the lubricant for the journal bearing?
Sure. Water can be used. Why not? The viscosity of water is very much less temperature dependent than the viscosity of hydrocarbons. But it is very much less viscous than the majority of the commonly used hydrocarbons. But sure, you can use water.
But once the temperature reaches boiling point.
Okay. Yeah. Yeah, but yeah, water's fine. You can use air, but you do the sums. Yeah, I mean, there's nothing specific in the Sommerfeld number and all those charts and so on. That's the great virtue of using a non-dimensional quantity. That you plug in the appropriate viscosity.
Right, wonderful. Got quite a few more questions coming through.
Okay.
I'll sprint through them. So BABIT is a reliable and tested methodology for bearing protection. Could you expand on more recent developments in material selection?
Well, if we're talking about steadily loaded hydrodynamic bearings, I mean, normally when you design a tribological pair, you're thinking of making one of the surfaces possibly sacrificial. So if there is wear, that you can replace one of the components relatively easily. Yeah. And usually the shaft is the more expensive component. And therefore you make the bearing the potentially sacrificial component. And normally that will be softer than the shaft. And it's general good practice, we would say, to not run like on like. So you don't make both components out of the same stuff. I mean, there are notable exceptions to that. But as a general rule, you would not make the two solid components out of the same material with the same, because there's always a propensity for them to pick up. Yeah. And in general, the bearing sleeve is the component that it's easier to replace. So you make that softer, and bear in mind you might have to replace it.
Yeah.
In terms of materials, well, obviously there are environmental concerns. We don't use lead now because of environmental concerns. So there's always an interest in new bearing materials and so on.
I think there are a lot of development in terms of materials in this day and age anyway. So I think it's an area that is evolving.
Yeah, I mean if you're thinking about polymers or marginally lubricated, you don't. I mean, obviously the one that everyone thinks of is PTFE. Well, PTFE's got potentially a very low coefficient of friction, but it's not a low wear material. It tends to wear out rather quickly. So it's not always the best polymer. Well, it rarely is the best polymer to use. Depends on the application. But, these things are always a compromise.
Yeah, you can't eat your cake and have it.
No. Not like Joe.
Okay, so then we have the other question that says, do you see any concerns or challenges for the bearings in hybrid and electric vehicles? Do you expect these bearing designs to be different?
Well, this was the topic of the meeting, the IMechE meeting last week. Well, interestingly, I mean, electric motor. It's always a good idea to match the characteristics of the bearing to the characteristics of the device into which you're fitting the bearing. Now, the point about electric motors is they produce very high torque at very low speed, which is why they're attractive for vehicles, of course. But that means they're not very attractive for hydrodynamic bearings, because hydrodynamic bearings have no load capacity at zero speed. So electric motors tend to use rolling element bearings, and transmissions tend to use invariably use rolling element bearings. Internal combustion engines can use hydrodynamic bearings because if you think of the torque speed characteristic, that builds up, that has a similar sort of shape to the load carrying capacity of a hydrodynamic bearing. So the two are kind of matched. Whereas as I say, the torque speed characteristic of an electric motor is pretty flat, or possibly descending. So as we move from internal combustion engines to electric propulsion, we're going to see more rolling element bearings. In hybrid vehicles, the cost of a hybrid vehicle, the cost is in the electrical supply. So the engine of hybrid vehicles, I mean, this is something that came out in this various talks, are likely to get simpler rather than more complicated. So because the engine can run at its sweet spot more continuously, it doesn't have to have such a broad band of operation. You can run the engine's just there to charge the battery, as it were. You can run the engine at closer to its optimum conditions, which means you can run the bearings close to their optimum conditions.
Yeah.
So hopefully you don't need particularly sophisticated solutions. And you can use thinner, less viscous lubricants and reduce the churning losses and the viscous losses.
Great. Thank you for that. Another question here is, do you have any formula to show the surface roughness, RA, effect? And that's basically, I think this individual is looking to see what the effect of roughness is between the shaft and the...
In a hydrodynamic bearing, but in a full fluid film bearing, the object, the exercise, is to make the fluid film sufficiently thick that the surface roughness of the two opposing surfaces is not critical. And that means that the so-called lambda ratio, which is the ratio of the fluid film thickness computed on the basis that the surfaces are smooth, compared to the joint roughness of the two surfaces, should be a factor of at least 3. And on that, if you're assured of that, then there's a pretty good chance that the surfaces will never come into contact. If the lambda ratio approaches 1, then the asperities on the two surfaces are going to know about each other, and the surfaces are going to interact in some way. Well, they might interact beneficially. You might get them to run in, so you actually smooth the surfaces off. Yeah. Or you might not. And then we start to think about the chemistry of the lubricant, whether you've got additives, what happens on the surfaces, and so on and so forth. So the thinner you make the film, that's why you put additives into the one of the reasons why you put additives into the base fluid to cope with these situations.
Okay, so I've got another question here from Dr. Williams' comment on reducing power losses. Can he comment on the power losses from oil seals, such as the normal
seals?
And the lip seals?
Oh dear. Well, no, not really. The first port of call when you want to reduce these losses is to reduce the viscosity. But there are costs associated with that. In terms of lip seals, I don't know how much of the loss comes from, as it were, solid contact. The whole object, the exercise, is to stop the fluid getting out. So part of the absorbed torque must go into effectively solid contact between the polymer or elastomer and the solid surface, I suppose. But and part of it is going to be because of viscous losses in the fluid. But I'm not sure how you split that up. Can't help, I'm afraid.
So it's factor, right?
Do you know anything about lip seals?
Well, not much. My tribology falls a bit more towards the medical side.
Oh, right. Okay.
So yeah, we've just got about under 4 minutes left.
Okay.
I've got just a comment and 2 other questions. I think there's an assistant here regarding the question on spiral groove, and it's saying that maybe to help on the spiral groove question, modeling of spiral groove bearings are normally steady state, i.e. hydrodynamic. Squeeze film contribution is from transient effects such as vibration, and normally very small in comparison to hydrodynamic effect.
Okay, well, I mean, the way I think of a spiral groove bearing is really it's a bit like a Rayleigh step bearing. I mean, the load carrying support, and we haven't talked about Rayleigh step bearings at all, but it's more like a thrust bearing. Actually, the actual mechanism that generates the lift in a spiral groove bearing. There's a very good book, perhaps the correspondent, the questioner knows, there's a very good book by a chap whose name escapes me, but is a Dutch chap who worked for Philips at Eindhoven. And they did a tremendous amount of work on spiral groove bearings. Wiedemann, his name is. That, I think, would be a good place to start.
Right.
But again, there's a huge amount in the literature. You know, you look through the research literature. Spiral groove bearings are, been widely investigated, both thrust bearings and journal bearings.
Okay, and then the final 2 questions. One of them says, what are the contributors in heat generation in bearing or heat added to oil in hydrodynamic bearings?
Well, essentially, it's it's the shear rate in the oil. I mean, if you work out, if you know what the viscosity of the oil is, and you know the dimensions of the bearing, and you know the shear rate, and so on, then you can work out the power being absorbed by the bearing, and the easiest assumption to make, although obviously it is a simplification, is to assume that all that heat is convected away by the oil. And if you know what the thermal capacity of the oil is, you know the specific heat of oil, and that doesn't vary from one oil to another, then you can work out the temperature increase. Yeah. Typically, if you do that for a hydrodynamic bearing, it's about 20 degrees centigrade. So the oil comes out of the bearing at about something like 20 degrees centigrade hotter than it went in. That would be a not untypical sort of example. And I mean, if you're thinking of a fully formulated lubricant, you don't want the lubricant to get above, 150 centigrade, something like that. It will start to degrade, it will start to oxidize, it will start to, things chemically will start to happen. Yeah. So that means that you don't want the oil to go into the bearing at anything more than about 120 degrees centigrade, something like that. I mean, that's a very rough sort of figure, but for ordinary for most hydrocarbons, that's, I think, still true. Yeah.
So I think we have run out of time, and there is a question here that asks about the lowest value of HMing that would be recommended for journal bearing. I think that depends on the design and the material.
Well, I think it goes back to this lambda ratio thing. Yeah. I mean, if you're prepared to pay for very good surfaces and very accurate components, you can get away with thinner oil films.
It's going to end up in a compromise on
it's always, I mean, everything. All engineering designs are compromises, aren't they? I mean, when it comes down to cost, of course. That's the ultimate.
Great. So I would like to thank you all for participating in this webinar, and thank you so much, Professor John Williams, for taking the time out, and also for just answering the questions adequately.
All right.
Very
good.
grateful. Right. Thank you very much.